Welcome to Scoli Sleep Stories. Before we begin, take a moment to get comfortable. Let the day soften around you, and settle in for a calm documentary made for curious minds. If these stories help you rest, learn, or simply enjoy a quieter part of the day, please consider liking this episode and subscribing to the channel. Now, when you are ready, let us begin. Chapter 1: A Circle in the Quiet. Above a wide stretch of dark water, the moon rests in a clear evening sky. Its pale light lies gently across the pond, touching the reeds along the bank and the smooth stones beneath the shallows. The air is still. The moon's reflection remains almost unbroken, floating quietly upon the water. Then a small pebble slips from the shore. It enters the pond with a soft sound, and the reflection trembles. From the place where the pebble disappeared, a ripple begins. It travels outward in a widening ring, followed by another, and then another. Each ring becomes broader and fainter as it moves across the pond. In time, the ripples fade, and the water grows calm once more. The moon above looks round. The ripples below look round. Nearby, the rim of a wooden bowl catches a narrow line of moonlight. A cartwheel leans against a quiet wall, its curved edge forming another familiar shape among the shadows. Circular forms appear throughout human life. We see them in wheels and bowls, rings and round windows. We notice them in shadows, in the opening of a vessel, and in the widening ripples made by falling rain. Even the moon appears to us as a bright, round disk. The moon itself is not flat. It is roughly spherical, yet when viewed from Earth, it presents the appearance of a circle filled with pale light. Long before the earliest surviving mathematical writings, people noticed and used circular forms. They shaped round vessels and ornaments. They watched the heavens. They left curved marks in clay, wood, stone, and earth. We cannot know exactly when someone first paused to think carefully about a circle, nor can we establish that the circle was humanity's first mathematical shape. That beginning lies beyond recorded history, where many ordinary human discoveries have left no written trace. Still, it is easy to imagine a hand drawing a curve in smooth sand. A fingertip begins at one place, it moves around, bending gently until it returns to where it started. The line closes upon itself. Inside it rests a quiet region, separated from the sand beyond. The shape seems simple, yet within it are several ideas that people would gradually learn to name. In mathematics, a perfect circle is not merely anything that looks round. It has a precise meaning. Imagine a single fixed point on a flat surface. It might be marked by the end of a stick pressed lightly into sand, or by a tiny dot upon a sheet of paper. The center need not be large or prominent. It is simply the point around which the circle is arranged. Now imagine many other points surrounding it. Every one of these points lies at exactly the same distance from the center. Together, all those equally distant points form the circle. This is the mathematical circle, a set of all points in a flat plane that are the same distance from one fixed point. That equal distance also has a name. It is called the radius. A radius may be pictured as a straight thread stretching from the center to the circular boundary. If one end of the thread remains fixed at the center while the other moves around it, the moving end traces a circle. Wherever that end travels, the distance back to the center remains unchanged. A small circle has a short radius. A larger circle has a longer radius. Yet the underlying idea is always the same. Every point on the circle is one radius away from the center. We can also imagine another straight line, one that crosses the circle completely. It begins at a point on the boundary, passes directly through the center, and continues to a point on the opposite side. This straight line segment is called the diameter. The diameter travels from the boundary to the center, and then from the center to the boundary again. For that reason, its length is equal to 2 radii. One radius carries us halfway across the circle. A second radius completes the journey. There is another quiet distinction to notice. It lies between the words circle and disk. In careful mathematical language, the circle is the boundary itself. It is the curved edge formed by all the points that are equally distant from the center. A disk includes both that boundary and all the space inside it. A ring may suggest a circle, because our attention rests upon its round boundary. A round-filled surface may suggest a disk, because it includes the whole region within the edge. In everyday conversation, people often use the word circle for both meanings. Usually there is no confusion. Mathematics simply offers two separate words for the moments when the difference matters. The perfect mathematical circle belongs to the world of ideas. The circles we meet in the physical world can come very close to that ideal, but they are never quite the same. A wheel may look circular, though its rim contains tiny irregularities. A bowl may seem perfectly round even while its surface holds subtle marks left by tools and hands. A ripple may be disturbed by wind, reeds, stones, or other ripples. Even a line drawn with great care has some thickness. The ideal mathematical circle, by contrast, is imagined as an exact boundary. Natural and manufactured circles are therefore approximations. They are close and useful reflections of a perfect form. Their small imperfections do not make them less beautiful. Instead, they reveal how one clear mathematical idea can be echoed in wood, water, metal, clay, shadow, and light. Perhaps this is one reason people have returned to circular forms across so many centuries. A circle can be suggested with the simplest of tools. A cord held at one end can guide a mark around the center. A wheel can turn around its middle. A vessel can become round beneath steady hands. A ring can surround an open space, and the shape is easy to recognize. We recognize it in a bowl before us and in the apparent disk of the distant moon. We see it in an object made by careful craft, and in a ripple that lasts for only a few moments. One circle may be small enough to rest upon a fingertip. Another may spread across the surface of a cond. The sizes differ, the materials differ, yet the familiar roundness remains. For now, the circle is not a problem to be solved. It is simply a shape to notice. We may notice its center resting quietly in the middle. We may imagine the radius reaching outward to the edge. We may picture the diameter passing all the way across, through the center from one side to the other, and we may remember the distinction between the circle, which is the boundary, and the disk, which includes the region within. At the edge of the pond, someone lifts the wooden bowl and runs a fingertip slowly around its rim. The finger follows the curved boundary, moving onward without meeting a corner. It returns at last to the place where it began. Or perhaps on another shore, and in another age, someone presses a fingertip into cool sand. The hand traces a curve around a chosen center. Slowly, the mark bends back toward its beginning. The circle is now complete. For a moment, it rests there in silence. A simple boundary surrounds a still patch of sand. The center may be marked, or it may remain only in the imagination. The radius may be measured, or merely sensed. The diameter may be drawn across, or left unseen. Then, as a fingertip follows the curved edge one more time, another thought quietly arises. Once a circle has been drawn, how might someone measure the journey around it? Chapter 2. The Measure That Returns. How far is it around? The question rests beside the circle as naturally as a smooth stone beside a pond. A fingertip can follow the rim of the wooden bowl. The journey curves gently onward until the finger returns to the place where it began. Yet a fingertip does not easily tell us the length of that journey. To discover the distance, we need a way to carry the curved path into a form that can be measured. Imagine a clay jar standing on a broad wooden table. Its rim is nearly circular, shaped by the steady hands of a potter. Beside the jar lies a length of soft cord. One end of the cord is placed against the rim, then the cord is guided carefully around the curve. It passes along the far side of the jar, comes around once more, and finally reaches its starting point. A small mark is made where the wrapped length ends. The cord has now followed the circle exactly once. That distance around a circle is called its circumference. The word may sound formal, but the idea is simple. The circumference is the length of the circle's boundary. It is the path traced by an ant walking around a round plate, the outer edge of a coin, or the line followed by a cord wrapped once around a barrel. The cord is lifted from the jar and laid straight across the table. What was curved around the rim has become a simple length. We can place marks beside it, compare it with a measuring rod, or hold it beside another cord. There is another useful measurement to make. Imagine a straight line across the widest part of the jar's rim, passing directly through its center. The distance from one side of the circle to the opposite side through the center is called the diameter. A second cord can represent this distance. It is stretched across the mouth of the jar from one edge to the other, passing over the center. Then it too is placed on the table. Now the two lengths can be compared. There is the long cord that traveled around the rim and the shorter cord that crossed the circle through its center. Place the diameter cord against the circumference cord once. It covers one part of the longer length. Place it down a second time, end to end with the first. Then place it a third time. 3 diameters reach almost to the end of the circumference cord, but not quite. A small length still remains. The distance around the circle is a little more than 3 diameters. A little more than 3 diameters. This is true not only for the clay jar, it is true for every exact circle, whether large or small. The circumference is not exactly 3 times the diameter. 3 diameters come close, but the circle's boundary continues a little farther. With more careful mathematics, the comparison begins with the number 3.14159, and more digits follow. So the circumference is approximately 3.14159 times the diameter. It is enough to notice the gentle shape of the answer. There are 3 whole diameters followed by a smaller remaining part. A value that is close to an exact value, though not exactly equal to it, is called an approximation. Saying that the circumference is about 3.14 times the diameter is an approximation. It is very useful, even though it does not reveal the full, unending number. There is another way to watch the circumference become a straight distance. Imagine a wooden wheel resting on a level path. A small spot on its rim is marked with chalk at the place where it touches the ground. A second chalk mark is made on the path directly beneath it. The wheel begins to roll slowly and evenly. The marked spot rises from the ground, travels over the top of the wheel, descends along the other side, and returns to the path. When the chalk spot touches the ground again, the wheel has completed one full turn. The distance between the 2 marks on the path is approximately 1 circumference of the wheel. In a complete turn, the wheel has laid out the distance around its rim as a straight journey forward. This works when the wheel rolls without slipping. In the physical world, however, a wheel may slip on a smooth or wet surface. It may sink into soft ground. Its rim may not be perfectly circular, or it may change shape slightly under weight. If any of these things happen, one turn may carry the wheel a somewhat different distance. The cord around the jar also brings small uncertainties. It may be thick rather than perfectly fine. It may stretch when pulled, or rest too loosely against the clay. The jar's rim may have tiny uneven places. Even the mark on the cord has some width, and the person reading it may place the mark a little to one side. These are not failures. They are simply part of measuring real objects. Every physical measurement contains some small amount of error. Greater care, smoother objects, thinner cords, and finer marks can reduce that error. Yet no physical cord, wheel, ruler, or mark can reveal infinitely many digits of the number hidden in the comparison. Still, the central observation remains clear. The circumference is a little more than 3 diameters. When one length is compared with another by division, that comparison is called a ratio. We can divide the circumference by the diameter and ask how many diameters fit into the distance around the circle. The answer begins 3.14159. Its complete nature is still waiting farther along our path. For now, the cords can be gathered and carried to other circular things. A soft cord is wrapped around the rim of a small cup. It is marked, lifted away, and straightened beside the cup's diameter. Another cord passes around the broad circular edge of a barrel. A longer cord follows the rim of a cartwheel before being laid out carefully along the ground. The cup is small. The barrel is broad. The cartwheel is broader still. Their circumferences are different, and their diameters are different too. Yet each time the same simple actions can be repeated. Wrap the cord, straighten it, compare it with the diameter. The measurements may not be perfect. The cup may not be an exact circle. The barrel may be slightly uneven. The cartwheel may bear the marks of use. Still, each comparison settles into the same quiet neighborhood, a little more than 3 diameters. The objects change. The cords lengthen and shorten. The circles widen and diminish. And softly, the same comparison returns. Chapter 3. A ratio hiding everywhere. The same comparison returns because every ideal circle in ordinary flat geometry shares one enduring relationship. Imagine the cup, the barrel, and the cartwheel resting quietly beside one another. Their rims are different sizes. The cord wrapped around the cup is short enough to hold easily between 2 hands. The cord around the barrel stretches farther. The chord following the cartwheel reaches farther still. Each chord measures a different circumference, and each object has a different diameter. Yet when the circumference of each circle is divided by its own diameter, the result is always the same constant. That constant is called pi. Pi is usually represented by the Greek letter pi. Its central relationship can be written simply: pi equals c over d. Here c means the circumference, the distance all the way around a circle. The letter d means the diameter, the straight distance across the circle through its center. Divide the circumference by the diameter, and the answer is pi. Its decimal form begins 3.141592653589793. The dots tell us that the digits continue. Their deeper story will come later. For now, it is enough to notice that a circle's circumference is a little more than 3 times its diameter. More precisely, the circumference is pi times the diameter. This relationship remains the same whether the circle is as small as a ring drawn in sand or as broad as an imagined circular lake. It applies to the rim of a tiny lens and to the outline of an enormous wheel, provided that we are considering ideal circles in ordinary flat geometry. The reason becomes clear through the simple act of enlarging a drawing. Suppose a small circle is copied at twice its original size. Every length in the new circle becomes twice as long. Its diameter doubles. Its circumference doubles as well. If the first diameter were 1 unit and the first circumference were pi units, then the enlarged diameter would be 2 units and its circumference would be 2 pi units. Both lengths have changed by the same scale factor. Because they have grown together, their ratio has not changed. The same thing happens if the circle is made 10 times larger. Its diameter becomes 10 times greater, and so does its circumference. If the circle is reduced to half its former size, both measurements become half as long. Enlarging or shrinking changes the lengths, but the relationship between those lengths remains steady. A silver ring, a millstone, and a broad ripple spreading across still water may differ greatly in size, yet the ideal circle represented by each carries the same proportion. The distance around compared with the distance across is always pi. There is another familiar length within a circle. It is called the radius. The radius runs from the center of the circle to its edge. 2 radii placed end to end form 1 diameter, so the diameter is twice the radius. D equals 2r. Because the circumference is pi times the diameter, the same relationship can also be written using the radius. C equals 2 pi r. Read gently in words. This says that the circumference equals 2 times pi times the radius. It is not a different principle. It is the same quiet relationship in another form, useful when the radius is easier to measure or imagine than the full diameter. Pi appears not only when we measure the boundary of a circle, but also when we measure the space enclosed within it. That enclosed space is the circle's area. If the radius is represented by r, then the area is a equals pi r squared. The small raised 2 means that the radius is multiplied by itself. In other words, the area equals pi times the square of the radius. Pi can therefore be found in another way, by dividing a circle's area by the square of its radius. The same constant that appears along the rim also helps describe the entire round surface within it. It may be tempting to imagine pi as a long chain of tiny digits somehow hidden inside a wheel, a coin, or a painted ring. But pi is not literally written inside physical objects. It is a mathematical relationship describing ideal circles. The digits are one way of expressing that relationship, not a material thread concealed within the rim. An ideal circle is perfectly round. Every point on its circumference lies exactly the same distance from its center. Physical objects can approach this form very closely, but they are never perfect mathematical circles. A handmade bowl may have minute irregularities. A metal coin may bear tiny marks along its edge. A wheel may bend slightly beneath its weight. A ripple may meet a reed, a stone, or a breath of wind. Even the finest measuring instrument has limits. Still, ideal circles provide highly accurate models for many real objects. Pi allows builders, craftspeople, scientists, and anyone measuring a round form to describe such objects with remarkable precision. The physical circle may be imperfect, yet the ideal relationship offers a steady guide. There is one gentle boundary to keep in mind. The familiar circumference to diameter ratio belongs to Euclidean geometry, the ordinary geometry of a flat plane. On a curved surface, familiar circular measurements can behave differently. A circle traced on a globe, for example, follows the curvature of the sphere rather than lying on a flat sheet. When such a circle becomes large enough, The relationship between its circumference and its diameter may differ from the relationship found in a flat circle. This does not diminish pi. It simply reminds us that geometry describes a setting as well as a shape. On an ordinary flat plane, every ideal circle has the same circumference to diameter ratio. Small or large, inked or imagined, each returns to the same constant. And so the chords beside the cup, the barrel, and the cartwheel were tracing more than 3 separate measurements. They were approaching one shared proportion. The chords differed in length, the objects differed in size, yet the comparison beneath them remained unchanged. A round divided by a cross gives pi. Long before the symbol pi was chosen, and long before anyone wrote its decimal digits, this relationship was already present wherever people worked with circles. It was there in wheels, jars, wells, columns, and round fields. Ancient builders and craftspeople encountered it through practical tasks, even though they had no modern symbol for it. To follow their early approximations, we can now step quietly backward in time to an age when pi had not yet been called pi, but the measure around a circle was already waiting to be understood. Chapter 4. Before pi had a name. Long before the familiar symbol pi appeared on a page, people were already making circles. A craftsperson might press a peg into the earth, fasten one end of a cord to it, and draw the cord taut. Then, moving slowly around the fixed center, the craftsperson could guide the free end through the soil and leave behind a rounded line. A builder might mark a circular foundation with chalk or charcoal. A potter, turning clay beneath practiced hands, could watch a vessel become round without writing an equation. Wheelwrights shaped rims, metal workers formed rings. Surveyors measured wells, towers, and plots of land. In all these tasks, the relationship we now call pi was quietly present. It did not need a name in order to exist. The boundary of a circle was a little more than 3 times its width, and anyone working carefully with round objects could meet that relationship through measurement. Imagine a cord laid across a wooden wheel, passing through its center from one side to the other. This gives the wheel's diameter, or its width through the middle. Now imagine another cord wrapped carefully around the rim. This follows the circumference, the returning boundary of the wheel. The 2 cords could be placed beside one another. Knots, charcoal marks, or worn measuring lines might help with the comparison. The longer cord would measure a little more than 3 times the shorter one. The result would not be perfectly exact. Real cords stretch. Wooden wheels are not ideal circles. Charcoal lines have thickness. Pegs can shift in soft ground, and a hand may not hold the cord at precisely the same tension each time. Yet the comparison could still be useful. For many practical tasks, usefulness mattered more than a long sequence of digits. A builder did not need every decimal place of pi to estimate the material required for a round wall. A potter did not need a formal theorem to judge the size of a lid. A craftsperson making a rim could rely on a familiar procedure that had worked many times before. Convenient whole numbers and fractions could relate a circle's width to its boundary or help estimate the area inside it. Such numbers were easier to remember, teach, and use. If a rule gave an answer close enough for the work at hand, it could be passed quietly from one worker to another and from one generation to the next. Such a method is called a practical rule. A practical rule is a procedure that works well enough for a particular task, even when it is not accompanied by a proof. It may grow from experience, repeated measurement, and careful observation. The worker follows the steps and receives a dependable result, within the accuracy that the work requires. A proof is something different. In mathematics, a proof is a logical demonstration showing that a mathematical claim must be true. It does not depend only on one wheel, one cord, or one successful building. It connects a sequence of reasons so that the conclusion follows from them. Practical rules and proofs can support one another, but they are not the same. A craftsperson may know from experience that a certain measurement produces a well-fitted rim. That knowledge is genuine and valuable. A mathematician may later explain why a related rule works, how close its result comes to an exact value, and where its limits lie. One kind of understanding grows through repeated practice. Another grows through formal reasoning. Across the long history of pi, both have played a part. That history also includes notation. Notation means the symbols used to record mathematical ideas. Today, the Greek letter pi can express the circle's constant ratio with a single familiar sign. A short mathematical expression can preserve an idea that would otherwise require many words. Earlier communities did not use this modern notation. They had their own words, marks, diagrams, number systems, and methods of calculation. Some rules may have been written on papyrus or clay, others may have been scratched onto a wax tablet, marked in charcoal, or spoken aloud during work. The modern symbol pi did not become standard until the 18th century. By then, people had already been measuring and studying circles for thousands of years. The mathematical relationship came first. Its familiar symbol arrived much later. So the history of pi is not a single path beginning in one place. It is more like many quiet paths crossing different landscapes and approaching the same open ground. In one settlement, builders might need to plan a circular structure. Elsewhere, someone might measure a rounded boundary. A wheelwright could compare the widths and rims of wheels. A potter could judge the proportions of a vessel. Record keepers might preserve a useful rule so that it could be applied again. Different communities met circles through different needs. Their methods could be rough or careful, written or remembered, practical or increasingly formal. Some approximations may have been sufficient for ordinary work, even though they did not express pi exactly. Practical accuracy and formal mathematical understanding are not identical. A rule may produce a useful answer without revealing the full reasoning behind it. In the same way, a person may construct a fine circle without stating its circumference to diameter ratio as a precise number. Much of this early work has disappeared. Wood decays, wax tablets are smoothed and reused, charcoal fades. Marks drawn on the ground vanish beneath rain, wind, footsteps, and new construction. Spoken instruction may pass through many generations without leaving a document behind. The written records that survive preserve only part of ancient mathematical practice. A papyrus, a tablet, or an inscription offers a narrow view into a much larger world of daily knowledge. We may see one recorded method while many unrecorded methods remain beyond our reach. For this reason, the history of pi asks for patience and humility. When archaeologists find an ancient circular monument, its shape alone does not prove that its builders used one particular numerical approximation for pi. A well-made circle shows care, skill, and planning, but it does not reveal every calculation behind the work. People can form circles with chords and pegs, without expressing the ratio between circumference and diameter as a precise number. A builder may follow a dependable procedure without leaving a written explanation. Measurements taken from old and weathered structures may also allow more than one interpretation. It is therefore not justified to assign exact mathematical knowledge to prehistoric people unless evidence supports the claim. Admiration does not require exaggeration. Ancient makers deserve to be understood through what their works and surviving records truly show, rather than through modern ideas placed upon them. Pi was not discovered in one sudden moment, and it did not belong to one civilization. Its history unfolded gradually through practical measurement, approximation, proof, notation, and much later, computation. Each part of that history added something different. Builders and craftspeople developed useful procedures. Record keepers preserved numerical rules. Mathematicians sought clearer reasoning and closer approximations. New notation made relationships easier to record and share. In a later age, machines would carry calculation far beyond what hands alone could accomplish. But near the beginning of the story, there was often only the task itself. A cord was drawn tight. A peg was pressed into soil. A charcoal mark was placed carefully on wood or stone. A boundary was followed and a width was measured. Across open land, measuring cords could divide fields, set out foundations, and restore boundaries. Their fibers grew smooth with use, while their knots held familiar intervals. When a cord was laid across a circular space, it gave an approximate diameter. When it was bent around the edge, it followed the circumference. The hidden ratio remained the same, even when no one spoke its modern name. In the lands beside the Nile, measuring cords belonged to a landscape repeatedly shaped by water. The river rose over parts of the valley and later retreated. As the water withdrew, fields appeared again beneath the open sky, ready to be marked and measured once more. There, among cords laid across the earth, the work of builders and surveyors, and the records kept by scribes, we find early written clues to the practical measurement of circles. Chapter 5: Circles Beside the Nile. Along the banks of the Nile, the rivers rising shaped both the land and the lives of those who lived beside it. Water spread across the valley, leaving rich, dark silt behind. When the river receded, the fields emerged beneath the sun once more. Some boundaries had grown faint. Paths and markers might have shifted. Patient hands were needed to measure the land again. A cord could be stretched between pegs. A line could be traced through dry sand. Measurements could be recorded in dark ink upon a pale sheet made from papyrus fibers. Papyrus was a writing material made from the papyrus plant, which grew in the wetlands of the Nile. Its inner stalk was cut into thin strips. These were laid in crossing layers, then pressed, dried, and smoothed. The finished surface was light enough to carry and broad enough to hold long columns of writing. Upon it, trained scribes preserved accounts, instructions, stories, and calculations. A scribe was a person trained to write and keep records. In ancient Egypt, scribes held an important place in administration and learning. Their records could concern grain, labor, taxes, buildings, or parcels of land. Some scribes also copied mathematical examples, preserving useful methods that had already passed through earlier generations. One such scribe was named Ahmes. Around 1650 BCE, Ahmes copied the collection now known as the Rhind mathematical papyrus. He indicated that the material came from an older source. The document that survives is therefore one part of a much longer chain. Older knowledge was copied carefully, so that its working procedures might remain available to those who followed. The papyrus contains many practical mathematical problems. Among them are questions about quantities, divisions, slopes, storage vessels, and areas. Problem 50 concerns the area of a circular field. Imagine such a field resting quietly near the river. Its boundary curves gently back toward itself, enclosing a patch of fertile ground. To estimate how much land lies inside that boundary, the papyrus provides a working rule. Begin with a circle whose diameter is 9 units. The diameter is the straight distance across the circle through its center. From that diameter of 9, remove 1/9. 1/9 of 9 is 1, leaving 8. Then imagine a square whose side is 8 units long. The area of that square is 8 multiplied by 8, or 64 square units. The rule therefore gives the circular field an area of 64 square units. There is no need to hold the calculation tightly in mind. Its motion is simple and steady. 9 becomes 8. 8 is multiplied by 8. The result is 64. The procedure replaces a curved shape with a square whose area can be found through straightforward multiplication. No modern symbol for pi appears. There is no long decimal written across the papyrus. There is only a practical sequence. Take the diameter, reduce it by 1/9, and square what remains. Modern mathematics allows us to look back at this rule from another direction. Today, the area of a circle is written as a equals pi times r squared. In words, the area equals pi multiplied by the radius squared. The radius is half the diameter, so a circle with a diameter of 9 units has a radius of 4.5 units. If we translate the Egyptian result of 64 square units into the modern formula, we can ask what value of pi would produce that answer. The value implied by the procedure is 256 divided by 81, or approximately 3.1605. This is sometimes described as the rule's effective value of pi. An effective value is a value implied when an older procedure is translated into modern mathematical notation. It is not necessarily a number that the ancient writer explicitly named or defined. That distinction is important. The Rhind mathematical papyrus does not declare that pi is exactly 256 divided by 81. It does not present pi as an abstract constant in the modern sense. Instead, it gives a working method for finding the area of a circle. The fraction 256 divided by 81 is a modern interpretation of what that method implies. The approximation is slightly larger than the value of pi used today, about 3.14159. For a circle 9 units across, the modern formula gives an area a little less than 64 square units. The ancient rule is not highly accurate by modern standards, especially when great precision is required. Even so, it is reasonably close. For practical purposes, and in circumstances where the original measurements might themselves be approximate, it could offer a useful estimate. Nor should one surviving document be treated as a complete description of Egyptian practice. We cannot assume that every Egyptian builder, surveyor, craft worker, or official used this exact method. Different tasks may have encouraged different habits, and much ancient knowledge has not survived. The The rind mathematical papyrus is precious because it gives us one clear written window into the past, not because it records every method once known beside the Nile. Still, the old page tells us something quiet and enduring. Long before the circle was joined to the symbol pi, people were finding ways to work with curved boundaries. They observed, measured, simplified, and recorded. A circular field could be compared with a square. A useful rule could be copied from an older source. Knowledge could travel from one careful hand to another, across many centuries. The reed ink has long since dried. The fields known to Ames have passed through countless seasons of river water, dry sand, and sun. Yet the procedure remains. 9 becomes 8, and 8 becomes 64. Behind that practical rule, modern readers can glimpse an approximation of the same constant hidden within every circle. Beyond the Nile Valley, other rivers supported other cities and other traditions of calculation. The pale fibers of papyrus now begin to fade from view, along with reed ink and newly measured fields. Farther east, in the warm air of Mesopotamia, scribes worked upon a different surface. There, numerical knowledge was pressed into soft clay. Chapter 6. The Tablets of Babylon. In Mesopotamia, between and around the rivers Tigris and Euphrates, clay was always close at hand. It gathered along river banks and irrigation channels, soft enough to shape when damp, and firm enough to endure when dried. From this ordinary earth, scribes made lasting surfaces for writing. Imagine a quiet room in one of the region's ancient cities. Low light enters through a doorway and settles upon a simple table. A scribe holds a small tablet in one hand and a cut reed stylus in the other. The clay is cool and yielding. With each careful press, the stylus leaves a small wedge-shaped mark. This writing system is now called cuneiform, a word meaning wedge-shaped. Its signs could preserve many kinds of knowledge. They recorded inventories of grain, accounts of livestock, legal agreements, letters, observations of the sky, numerical tables, and mathematical exercises. Once a tablet had been written, it might be left to dry in the sun, or baked more thoroughly. Some tablets were stored on shelves or placed in containers. Others were reused, discarded, buried, or broken. Through chance, circumstance, and the sheltering earth, a small portion endured. The surviving tablets offer narrow windows into a mathematical culture that extended across long periods, many cities, and changing traditions. They do not reveal everything Mesopotamian scribes knew, and they do not suggest that every scribe followed precisely the same methods. What remains is varied. There are school exercises, tables of numbers, worked examples, and practical calculations. One of the most distinctive features of Mesopotamian mathematics was its use of a base 60, or sexagesimal, number system. Our familiar decimal system is organized around powers of 10. 10 ones make 10. 10 tens make 100. A sexagesimal system, by comparison, is organized around powers of 60. At first, 60 may seem like a large number upon which to build a system, yet it has a quietly useful quality. It can be divided evenly in many ways. 60 is divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Because it has so many divisors, many common fractions can be expressed conveniently. Faint traces of this ancient habit remain with us. An hour is divided into 60 minutes, and a minute into 60 seconds. A complete circle is divided into 360 degrees, a number closely related to 60, and likewise rich in divisors. Whenever we measure time in minutes, or an angle in degrees, an echo of sexagesimal calculation continues into the present. Within this numerical world, Mesopotamian scribes also worked with circles. A builder might need to estimate a circular area. An administrator might compare quantities connected with round objects. A mathematical exercise might ask for a boundary or a surface. Each task required some usable relationship between the width of a circle and the distance around it. Some simple calculations effectively treated the circumference as 3 times the diameter. If a circular object had a diameter of 10 units, its circumference would then be taken as 30 units. The rule was direct, memorable, and easy to use. It was not exact, but a rough calculation did not always require exactness. Other surviving evidence points to a more accurate Babylonian approximation, corresponding to the fraction 25/8. In modern decimal notation, 25 divided by 8 is 3.125. This lies closer to the value we now call pi than the simpler value of 3. The contrast between these choices need not be viewed as a conflict. A value of 3 is convenient and quick. A value of 3.125 requires slightly more care, but gives a closer result. The choice could depend upon the problem, the local tradition, the historical period, or the degree of precision considered useful. It would be misleading to imagine that every Mesopotamian scribe knew and used 3.125 in every circular calculation. Babylonian mathematics was not one unchanging collection of rules. It developed across centuries and appeared in different cities and settings. The tablets that happen to survive form only a limited sample of a much larger mathematical culture. Many other tablets have disappeared. Many lessons were surely spoken rather than written. Some methods may have belonged to particular schools, professions, or places. The remaining wedges in clay can tell us a great deal, but they cannot make the ancient world uniform, nor were these approximations necessarily presented as modern statements about a single abstract constant. Today, pi is defined as the ratio of a circle's circumference to its diameter. Mathematicians can study that ratio independently of any particular wheel, field, jar, or building. Ancient scribes were often concerned instead with procedures. They needed a rule that could transform a known measurement into a useful answer. A scribe might copy a numerical table, learn a standard method, and apply it to a particular figure. The chosen value became part of the working rule. It could help settle an account, solve an exercise, or estimate a quantity. Precision, in this setting, had a purpose. Additional precision was valuable when the task called for it. At other times, a simpler value could be entirely adequate. The aim was often not to write an endless expansion of digits, but to make the circle manageable within the work at hand. So the clay tablets preserve not one Babylonian answer, but signs of thoughtful selection. 3 could serve as a simple estimate. 25/8, or 3.125, could provide a finer one. Both belong to the long human practice of bringing curved forms within reach of number. The scribe's stylus lifts from the damp clay. Across the tablet, ordered rows of wedges remain. Nearby, other tablets rest in the low light, each holding a small arrangement of words, quantities, and procedures. A circle cannot be unfolded into a straight boundary without some act of mathematical translation. Yet the scribes found practical ways to describe it. They chose values suited to their purposes and preserved those choices in clay. In time, another approach would ask a more formal question. Instead of selecting a convenient value from custom or experience, could someone place firm limits around the circle's measure? Could straight-sided figures, whose edges were easier to calculate, reveal something about a curved boundary? The shelves of clay tablets slowly recede, the stylus grows still, and the path of the circle turns toward polygons, many-sided shapes drawn carefully within and around it, enclosing its hidden ratio between two known measurements. Chapter 7: Archimedes and the Polygons. From the ordered marks of Babylonian tablets, the story of circular measurement travels westward, across lands and quiet waters, toward the island of Sicily. There, beside the Mediterranean Sea, stood the ancient city of Syracuse. In the 3rd century BCE, Syracuse was home to Archimedes, a mathematician who studied shapes, numbers, balance, motion, and many other subjects with patient attention. Imagine a peaceful courtyard within the city. Sunlight rests upon pale stone. Beyond the walls, the sea moves in long, even swells. On a polished tablet, or perhaps in a level patch of fine sand, someone has carefully traced a circle. The old question remains: how long is the curved boundary around this circle? That boundary is the circumference. The diameter is the straight distance across the circle, passing through its center from one side to the other. When the circumference is divided by the diameter, the result is the constant now called pi. Archimedes did not use the modern Greek symbol for pi. That notation would appear many centuries later. Yet in his work Measurement of a Circle, he developed a rigorous geometric method for placing the value of pi between two dependable limits. He began not with another curve but with straight lines. Inside the circle, picture 6 points spaced evenly around the boundary. Now join each neighboring pair with a straight segment. The result is a regular hexagon, a 6-sided figure with sides and angles arranged in the same repeating pattern. A polygon is a closed shape made from straight line segments. A triangle is a polygon with 3 sides. A square has 4 sides. A hexagon has 6. Because straight segments can be measured and calculated more easily than one continuous curve, polygons can serve as calm, orderly companions to the circle. The hexagon in our picture lies entirely within the circle. Each of its 6 corners touches the circular boundary. A polygon placed inside another shape and touching its boundary is called inscribed. Now imagine tracing a path around this inner hexagon. Each side travels directly from one point on the circle to the next. It takes a straight shortcut. The circle's boundary, by contrast, curves outward between those same points. Because the sides of the hexagon make these shortcuts, the total distance around the hexagon is less than the distance around the circle. The total distance around a polygon is called its perimeter. To find the perimeter, one adds the lengths of all its sides. For a regular polygon whose sides are all equal, the process is especially orderly. The length of one side can be multiplied by the number of sides. And so, the perimeter of the inscribed hexagon gives a lower value. The circumference of the circle must be greater than that inner perimeter. Archimedes then turned his attention to the space outside the circle. Imagine a second regular hexagon surrounding it. This outer polygon is arranged so that each of its sides touches the circle from the outside. A polygon placed around another shape in this way is called circumscribed. The circle fits within the outer hexagon, resting against each of its 6 sides. The hexagon's corners extend beyond the circle, reaching into the surrounding space. A journey around this outer hexagon would be longer than a journey around the circular boundary. Its sides do not take shortcuts through the circle. Instead, they form a larger enclosure around it. The perimeter of the circumscribed polygon is therefore greater than the circumference of the circle. Now the unknown curved length has been gently enclosed. The perimeter of the inner polygon is too small. The perimeter of the outer polygon is too large. Between them lies the circumference of the circle. There is a quiet serenity in this idea. Archimedes did not need to straighten the curved boundary or measure it directly. Instead, he placed the unknown length between 2 quantities that could be calculated. It is as though 2 carefully built walls stand on either side of a path. The path may not yet be measured exactly, but it cannot pass beyond either wall. Because pi is the circumference divided by the diameter, these limits on the circumference also place limits on pi. Divide the inner polygon's perimeter by the circle's diameter, and the result is lower than pi. Divide the outer polygon's perimeter by the same diameter, and the result is higher than pi. The hidden ratio is held between 2 known values. This was more than a convenient estimate. It was a geometric argument showing why the answer had to remain within a definite range. Earlier approximations could be useful for building, surveying, or keeping accounts. Archimedes provided a carefully reasoned structure. There was a lower bound beneath the desired value and an upper bound above it. The 2 hexagons, however, still look noticeably different from the circle. The inner hexagon has 6 broad sides, each cutting across part of the curve. The outer hexagon opens into 6 wide corners. There is still considerable space between the polygons and the circle they enclose. A finite-sided polygon does not literally become a circle. However many sides it has, if their number is finite, its boundary is still composed of straight segments. Archimedes' method did not turn a polygon into a true curve, nor did it create an exact decimal expansion of pi. Modern decimal notation belonged to a much later age. What the method offered was a path of steady refinement. Each side of the inner hexagon could be divided through careful geometric work, producing an inscribed polygon with 12 sides. The outer hexagon could likewise be replaced by a circumscribed polygon with 12 sides. These new boundaries would follow the circle more closely. The 12-sided inner polygon would still take small shortcuts across the curve, but those shortcuts would be gentler than before. Its perimeter would remain below the circumference, though it would come closer to it. The 12-sided outer polygon would still surround the circle. Its corners would still extend beyond the curve, but not as far as the corners of the 6-sided figure. Its perimeter would remain above the circumference while moving nearer to it. The lower and upper limits would draw together. Archimedes' achievement did not depend upon a sudden guess. Its strength came from repeated disciplined calculation. The same clear idea could be used again and again, each time replacing broad sides with smaller ones, and each time narrowing the interval in which the circumference and therefore pi had to lie. Later accounts of Archimedes' life include dramatic stories, among them differing reports about his death. Those accounts were written later, and their details vary in reliability. They are not needed here. The quiet mathematical work is remarkable enough. A circle rests in the sand. Within it lies one straight-sided boundary. Around it stands another. The inner shape measures too little, and the outer shape measures too much. Between them lies the curved circumference, and within that circumference waits the ratio now called pi. For a moment the three shapes remain together in the warm light, the inner polygon, the circle, and the outer polygon. Nothing moves, and yet the method suggests a patient journey. 6 sides can become 12, 12 can become 24. The straight edges grow shorter, the corners become less prominent. The lower and upper bounds move gently toward one another. The circle itself remains unchanged. Only the polygons become more attentive to its curve, and with each careful refinement, the hidden value is held within a narrower embrace. Chapter 8. Patient sides, closer bounds. The same calm process continues around the circle, traced in the sand. Archimedes began with hexagons, figures made of 6 straight sides. One hexagon rested inside the circle, with each of its corners touching the curved boundary. Another stood outside, enclosing the circle within its straight edges. The inner polygon gave a perimeter that was too short. The outer polygon gave a perimeter that was too long. Somewhere between those two measurements lay the circle's true circumference. Archimedes could not yet state its exact length, but he could hold it securely between one value below and another value above. Then patiently, he refined the shapes. In mathematics, refinement means improving an approximation step by step. It does not mean that the first result was worthless. A simple estimate may already be useful. Refinement simply brings that estimate closer to the value being sought, often by repeating a reliable method with increasing care. For Archimedes, 6 sides became 12, 12 became 24, 24 became 48, and 48 became 96. The rhythm is steady. 6, 12, 24, 48, 96. With each doubling, the straight edges became shorter and more numerous. Each new polygon followed the circle more closely than the one before it. The inner perimeter increased toward the circumference, while the outer perimeter decreased toward it. The distance between the two estimates grew smaller. The circle itself did not change, only the polygons became more attentive to its curve. A polygon does not become a circle merely because it has many sides. It remains a polygon, formed from straight segments meeting at corners. Yet a figure with 96 sides can fit so closely around a circle that from a little distance, its corners may seem almost to soften. More importantly for Archimedes, the perimeters of those many-sided figures provided far better estimates than the perimeters of the original hexagons. This was patient work. Archimedes had no calculator, and he did not use long decimal expansions in the way a modern mathematician might. He relied on geometry, ratios, and carefully controlled estimates. At every stage, he needed to be certain that the inner measurement remained below the true circumference, while the outer measurement remained above it. His purpose was not merely to offer a likely answer. He wanted to demonstrate that the answer had to remain between two known values. Those values are called bounds. A lower bound is a value known to be less than or equal to the target. An upper bound is a value known to be greater than or equal to the target. Bounds can be imagined as two quiet markers placed on either side of a path. Even if the exact position of a traveler cannot be seen, the markers tell us where that traveler must be, and the traveler's position becomes more closely known. After carrying his calculations through polygons with 96 sides, Archimedes established these bounds. 223 divided by 71 is less than pi, and pi is less than 22 divided by 7. In words, 223 divided by 71 is approximately 3.1408, and 22 divided by 7 is approximately 3.1429. Pi lies quietly between them. These decimal forms help modern readers recognize how close the two bounds are. Archimedes himself, however, did not carry out the work with modern decimal arithmetic. His reasoning used geometry and ratios, along with estimates chosen carefully enough that the true value could not escape the interval he had established. The fraction 22/7 may sound familiar. It has long been used as a convenient approximation to pi. It is simple to remember easy to use in practical calculations, and close to the true value. For many ordinary purposes, such an approximation may serve quite well, but 22/7 is not exactly pi. In Archimedes' result, 22/7 serves as the upper bound. It rests just above pi, rather than matching it perfectly. The difference is small, but it is real. This distinction need not make the approximation seem less valuable. An estimate does not have to be exact in order to be useful. A map may leave out the individual stones along a road and still guide a traveler. A measured chord may be accurate enough for careful work, even if it doesn't express every possible fraction of its length. The amount of precision needed depends on the purpose at hand. Sometimes a close estimate is enough. At other times, narrower bounds are desired. Mathematics allows both, as long as the difference between an approximation and an exact value remains clear. Archimedes' work reveals a larger idea as well. When a dependable method can be repeated, each refinement may bring the estimates closer together. 6 sides, 12 sides, 24, 48, 96. The inner boundary moves outward. The outer boundary moves inward. Between them, the circle's circumference remains steady. The sequence suggests that further work could narrow the bounds still more. More sides would mean shorter edges. Shorter edges would trace the curve more closely. The two polygonal perimeters could approach one another, enclosing the desired value within an ever smaller interval. It is tempting to imagine continuing this process until a polygon has infinitely many sides and simply becomes a circle. As a gentle picture, this can be helpful. It evokes straight edges growing ever shorter and corners becoming ever less noticeable. Modern mathematics, however, treats infinity with greater care. A polygon with infinitely many sides is not an ordinary final polygon waiting at the end of the sequence. There is no last step after 6, 12, 24, and all the doublings that might follow. Instead, modern mathematicians use the more carefully defined idea of a limit. They examine what happens as the number of sides increases without bound, and as the difference between the polygonal perimeters and the circle's circumference becomes as small as desired. That language came much later. Archimedes did not need the modern definition of a limit to achieve his result. He worked with a definite number of sides. He established definite upper and lower bounds. Through geometry and disciplined estimation, he gave a rigorous approximation of pi. So the circle remains in the sand. Within it lies the inner polygon, its 96 small edges reaching outward toward the curve. Around it stands the outer polygon, its own 96 edges drawing inward. The shapes are so finely divided that their separate sides are almost difficult to distinguish. The lower measure has risen, the upper measure has fallen. Yet together they hold it within a narrow interval. Pi cannot slip below 223/71, nor can it rise as high as 22/7. The hidden ratio has not been written in full. Still, its location is known more closely than before. This is the quiet strength of repeated refinement. It does not demand one sudden leap to a perfect answer. It permits understanding to grow through a succession of careful improvements. Each stage rests upon the one before it. Each new set of sides follows the curve a little more faithfully. In centuries to come, other mathematicians would continue this patient work in their own ways. The straight lines surrounding the circle would fade from the sand, then appear again in manuscripts, diagrams, counting rods, and careful written traditions across Asia. There too, scholars would study curved forms. They would develop their own methods, make their own refinements, and bring the enduring ratio of circumference to diameter closer into view. Chapter 9. Ideas Traveling Eastward. The straight-sided figures of the previous chapter seem to fade from the sand. Then, across great distances and many centuries, circles and careful measurements appear again. They are traced in ink on paper, arranged with counting rods, and written across narrow palm leaves filled with patient lines of thought. Yet the history of mathematics is not a single road leading neatly from one place to another. It is more like a broad landscape crossed by many paths. Some paths meet, some separate and meet again. Others run beside one another without ever touching. Mathematical ideas sometimes traveled through trade, scholarship, translation, and commentary. Travelers carried practical knowledge between communities. Scholars copied texts, translated unfamiliar words, and considered methods developed in other places. An idea recorded in one century might be studied again in another, far from the place where the surviving account began. But similar methods in distant places do not automatically prove direct transmission. Historians must remain careful. People studying the same kinds of problems may discover similar patterns independently. Wheels turn in many lands. The moon appears round above every horizon. Builders measure circular spaces, and astronomers observe recurring paths and cycles. When people face similar questions, they may sometimes find related ways of answering them. Circular mathematics developed in India, China, and other regions through distinct scholarly traditions. A mathematical tradition is a community's inherited and developing way of teaching, recording, and solving problems. It may preserve earlier knowledge while also allowing each generation to explain, question, apply, and improve what came before. China and India, of course, are not single moments or single schools. Each contains many centuries, regions, languages, communities, and ways of thought. Phrases such as Chinese mathematics and Indian mathematics can be useful, but they gather together a great variety of people and ideas. No single text or scholar can speak for the whole. In China, the ancient work known as the 9 Chapters on the Mathematical Art included rules for circular measurement. Its instructions became part of a long tradition of mathematical study. Later commentators returned to those rules, explained them, and improved them. A commentary is a later explanation or expansion of an earlier text. It may clarify a short instruction, describe why a rule works, compare possible methods, or offer a more accurate result. Through commentary, an old work can remain active across generations. The earlier words stay on the page, while later voices gather gently around them. One may imagine paper resting on a low table in quiet courtyard light. Ink settles into the fibers. Beyond the study, rain falls softly along the roof and darkens the stones. Inside, a reader moves between an older rule and a new explanation, testing each step with care. In India, scholars also studied circular measurement through their own varied traditions. Around the year 499 of the Common Era, the mathematician Aryabhata recorded a rule equivalent, in modern numerical form, to dividing 62,832 by 20,000. The result is 3.1416. The relationship can be pictured calmly. If a circle has a diameter of 20,000 units, the rule gives its circumference as 62,832 units. Dividing the circumference by the diameter produces the approximation 3.1416. This value lies very close to pi. Aryabhata's wording is generally understood as indicating an approximation, rather than claiming that the ratio ends exactly at those 4 decimal places. The number was a useful landmark, offered within its own mathematical setting and for its own purposes. Imagine the rule written along a palm leaf manuscript. The leaf is narrow, and the writing must be compact. A scholar sits in sheltered light while rain moves across the courtyard beyond. The numbers are considered slowly, perhaps checked and remembered, then passed onward through teaching and further study. There is no need to picture this as a contest between distant cultures. Aryabhata's value belongs to a particular place, period, language, and tradition. Elsewhere, other scholars worked within their own settings, guided by different texts and different mathematical needs. Other Indian mathematicians sometimes used the square root of 10 as a value for pi. It was not as close as 3.1416, but a less accurate approximation could still be useful in a particular context. Historical mathematics did not always seek the longest possible sequence of correct digits. Different approximations could serve different purposes. A teacher introducing a method might favor a convenient value. A practical calculation might require only moderate precision. Another problem might call for a closer estimate. The usefulness of an approximation depends partly on what the person using it is trying to do. Across these traditions, the circle remained the same quiet shape, its circumference curved around its center, and its diameter crossed from one side to the other. The ratio between them did not change, though the ways of describing and approximating that ratio varied. Our knowledge of this history is incomplete. Surviving texts reveal what some scholars knew and chose to record. They do not always show who first discovered an idea, how widely it circulated, or what knowledge passed orally from teacher to student. Manuscripts could decay or be lost. A work might survive only through a later copy or commentary. Silence in the surviving record does not prove that no one had considered a method before. It simply reminds us to speak with care. So the story of circular mathematics across Asia is not a relay race, with one culture handing a single answer to the next. It is a gathering of many sustained investigations. Some ideas traveled through trade, translation, scholarship, and commentary. Others may have arisen separately as people attended to the same enduring forms. For now, we remain in China, beside an older text and the later voices that studied it. There, one careful commentator named Liu Hui would return to the rules of the 9 chapters on the mathematical art, with straight sides placed inside a curved boundary, and each refinement following patiently from the last. He would find a way to bring the estimate closer. Chapter 10. Liu Hui's Quiet Refinement. In the China of the 3rd century, a scholar bends over an old mathematical text. Beside him lie a writing brush, dark ink, and smooth sheets of paper. The room is still, perhaps quiet enough to hear the faint movement of the brush as it crosses the page. The scholar is Liu Hui, a Chinese mathematician whose life is known mostly through his work. In the year 263 CE, he completed an influential commentary on an older collection called the 9 Chapters on the Mathematical Art. That work had developed over a long period, shaped by generations of mathematical thought. Many of the people who contributed to its tradition are no longer known by name. Liu Hui was a commentator, yet a commentator does much more than copy the words of an earlier text. A commentator explains, analyzes, and sometimes extends the work that came before. Liu Hui examined the methods in the 9 chapters, considered why they worked, and offered careful reasoning. Where an older rule supplied an answer, he tried to make the path toward that answer clearer. Among those older rules was a convenient approximation for circles. It treated the hidden ratio of circumference to diameter as 3. The rule was simple. If the diameter of a circular object measured 1 unit, its circumference could be taken as 3 units. For rough practical work, this might be adequate. It was easy to remember and easy to use. But Liu Hui understood that something was missing. The true circumference of the circle was a little longer than 3 diameters. To approach it more closely, he considered regular polygons drawn inside a circle. A polygon is a closed shape made from straight sides. A square has 4 sides. A hexagon has 6. A regular polygon has sides of equal length and corners of equal size. When such a polygon is fitted inside a circle, each of its corners touches the circular boundary. Between one corner and the next, however, the polygon follows a straight line, while the circle follows a gentle arc. With only a few sides, the difference is easy to see. A hexagon is clearly angular. Its straight boundary is shorter than the circumference surrounding it. Small curved regions remain between the polygon and the circle. Now imagine doubling the number of sides. 6 sides become 12, 12 become 24, 24 become 48. With each doubling, the straight edges become shorter, and the shallow arcs beyond them become smaller. The polygon begins to follow the circle more closely. Liu Hui repeated this process. It was an algorithm, meaning a defined sequence of steps for carrying out a calculation. Each stage supplied what was needed for the next. There was no need for a sudden guess or an unsupported leap. The estimate emerged gradually through an orderly process of refinement. One may picture the figures appearing beneath Liu Hui's brush, a circle, then an inscribed polygon resting within it. New lines divide the earlier form into smaller parts. Nearby, columns of numbers record the changing measurements. The brush pauses, returns to the ink, and moves again. The work required patience, but its central idea was calm and clear. Because the polygon remained inside the circle, its boundary gave a measurement below the circle's true circumference. As the number of sides increased, less distance remained between the straight boundary and the curved one. The estimate moved closer. Liu Hui did not merely carry out the calculation. He explained why repeated refinement improved the result. He considered the narrow regions left between the polygon and the circle, and showed how those regions diminished as the sides multiplied. Precision and explanation grew together. For a moment we can let the doubling pause. Around the polygon lies the circle. Between each short side, and each shallow arc rests a slender space. At the next stage, that space will be smaller. At the stage after that, smaller still. The polygon does not become the circle, but its measured boundary draws nearer and nearer to the circular boundary. Liu Hui's approach is conceptually related to polygon approximation methods developed elsewhere. Yet his work belongs to a distinct Chinese mathematical tradition, rooted in its own texts, language, questions, and methods of explanation. There is no need to suppose that he directly knew Greek mathematical work, nor should he be described as merely repeating Archimedes. People in different places can study the same enduring shape and discover related approaches, while following paths that were historically and culturally their own. Modern accounts often associate Liu Hui's extensive refinement with a value of pi around 3.1416. This is a remarkably useful approximation. If a circle had a diameter of 1 unit, its circumference would be estimated at about 3.1416 units. That is much closer than the older value of 3. The surviving discussion can be summarized in several ways. Modern reconstructions sometimes distinguish between values calculated at particular polygon stages and values reached through further reasoning. Some descriptions also include extrapolation. Extrapolation means observing a pattern in results that have already been calculated, and then using that pattern to estimate a value beyond the directly completed stage. Because modern summaries do not always separate these details in precisely the same manner, the exact values assigned to particular polygon stages can vary from one account to another. There is no need to linger among those competing reconstructions. The broad achievement remains steady and unmistakable. Liu Hui transformed a rough circular value into a reasoned process of improvement. He showed how straight-sided figures could approach a curved boundary, and how an estimate need not remain fixed when a dependable method could refine it. There is something quietly enduring in this kind of mathematics. It does not ask for every possible stage to be completed at once. It asks only for the next careful step. Draw, divide, calculate, compare, and then refine. With every repetition, the method becomes more precise. At the same time, the reason for trusting it becomes clearer. The calculation is not simply a collection of numbers. It is an explanation unfolding step by step. Liu Hui's commentary carried this way of thinking forward to later scholars. His work joined practical calculation with mathematical justification, showing not only what could be done, but why the procedure could be trusted. Through later copies and continued study, his patient reasoning remained present on the page. We can imagine the brush resting now beside the finished lines. Within the circle sits a many-sided figure. Its edges are so short that from a little distance, they nearly seem to form a curve. Yet a narrow difference remains, reminding us that the result is still an approximation. And so the process can continue. More sides, smaller spaces, a closer measure. From Liu Hui's steadily improving estimates, Chinese mathematics would move toward an exceptionally close fraction. It would be formed from two whole numbers, one placed above the other, and it would rest almost perfectly beside pi, without ever becoming identical to it. Chapter 11. Zhu Chongzi's Remarkable Fraction. Several generations after Liu Hui described his patient refinement of polygons, the study of circles continued in China. Earlier writings were copied and examined. Calculations were preserved, reconsidered, and improved. Each advance brought human measurement a little nearer to the smooth curve of the circle. Within this wider scholarly tradition lived Zhu Chongzi, from 429 to 500 CE. His work belonged not only to one individual, but also to a larger landscape of family, scholarship, and culture. Ideas passed between generations. Methods were studied and refined. Results that proved valuable were carried forward by later writers. Zhu Chongzi determined that pi lies between two remarkably close values, 3.141596 and 3.141597. There is no need to hold all those digits in mind. It is enough to notice that the two numbers are almost the same. Only the final stated digit is different. We might imagine them as two quiet stone markers set very near one another beside a road. Somewhere within the tiny space between them lies the true value of pi. The interval is so narrow that its entire width is only 1/10 millionth. This was an extraordinarily accurate result for its period. After centuries of measuring circles and improving approximations, pi had been placed within two nearly touching boundaries. Accuracy means closeness to the true value. One estimate is more accurate than another when it lies nearer to the number being sought. Yet closeness, even extraordinary closeness, is not the same as equality. A traveler may stand very near a bridge without standing upon it. Two lines may appear to meet from far away, while a fine separation remains between them. Zhuchongji is also associated with one of the most elegant approximations of pi ever written as a fraction. 355 over 113. A fraction is one integer divided by another. The number above the dividing line is called the numerator. The number below it is called the denominator. In this fraction, 355 is the numerator, and 113 is the denominator. The fraction simply asks us to divide 355 by 113. Its written form is small and balanced. There are two whole numbers and one short line between them. Nothing about its appearance seems elaborate, yet the value created by this division rests astonishingly close to pi. 355 divided by 113 begins 3.1415929203 and so forth. Pi begins 3.14159265 and so forth. Again, the individual digits need not be memorized. We can let them pass gently, like markings along a measuring cord. The important point is that the decimal expansion of 355 over 113 agrees with pi through the first 6 digits after the decimal point. After that, the two values begin to diverge. Their difference is about 0.0000267. That separation is less than 3/10,000,000ths. If the two values were paths crossing a wide, open plane, they would run so close together that an observer at a distance might see only one path. Only careful measurement would reveal that they remain distinct. And so 355 over 113 is remarkably close to pi, but it is not exactly pi. This distinction is gentle but important. The fraction provides a highly accurate approximation. It can stand beside pi in many calculations and produce a result that is almost indistinguishable in ordinary use. Yet almost indistinguishable does not mean identical. The fraction is like a narrow bridge reaching toward the true value. It carries us across nearly all the distance. It approaches so closely that the remaining space is difficult to see. Still, the final tiny separation remains. Closeness is not equality. There is another quiet uncertainty surrounding this achievement. The original detailed treatise that explains Zhuchongji's work has been lost. Knowledge of his results survives through later records, but the full account of how it was obtained is no longer available. For that reason, it would not be appropriate to invent a detailed method and present it as his. We know that Zhuchongji established the narrow bounds around pi. We know that he is associated with the fraction 355 over 113. We know that the approximation was exceptionally accurate for its period. But the complete sequence of reasoning that led to the result has not survived. The missing treatise is like a path whose beginning and ending can still be seen, while the footprints between them have faded. The destination remains clear, the precise journey does not. Some of the mathematical work may also have involved Zhuchongji's son, Zhu Gengzi. This possibility reminds us that knowledge often grows through family relationships, scholarly communities, and cultural traditions. One name may become closely connected with a result, while many conversations, lessons, copied texts, and shared methods surround that name. The achievement can therefore be admired both as an individual accomplishment and as part of a longer human practice. It emerged from people patiently studying the same enduring shape, generation after generation. Through later records, the result survived. The fraction passed across the centuries in an exceptionally compact form, 355 above and 113 below. It required very little space on a page, yet within that simple arrangement was a close image of the constant ratio found in every circle. Imagine for a moment a circular garden in the evening. A chord follows the outer boundary, measuring the circumference. Another chord crosses directly through the center, measuring the diameter. The circumference divided by the diameter gives pi. If 355 over 113 is used in its place, the calculation comes extraordinarily near the true answer. The difference may be far too small to notice in the imagined garden. It may disappear within the thickness of the cord or the softness of the ground. Mathematically, however, the difference is still present. The same is true for a wheel, a bowl, a ring, or a circle drawn lightly in sand. The fraction provides a beautiful and practical approximation. It approaches the hidden ratio with remarkable accuracy, but it does not become that ratio. Closeness is not equality. An approximation is useful because it can come near without claiming to be exact. For many centuries, fractions offered a clear and elegant way to approach quantities that could not be captured exactly by a simple division of whole numbers. A fraction could be written briefly, carried easily, and used again whenever a circle needed to be measured. Yet a fraction was only one path toward pi. Another path would eventually ask what happens when a calculation continues, not merely through many steps, but without a final step at all. From the narrow bridge of 355 over 113, the story now turns towards sums that continue onward term after term into the patient idea of an infinite series. Chapter 12. Infinite Series. A fraction such as 355 over 113 gives one remarkably close approximation to pi. It is compact, practical, and easy to carry from one calculation to another. Yet it remains a single fraction, and it must eventually stop. An infinite series offers a different path. Instead of choosing one fraction and ending there, a series begins with a number, then adds another, subtracts another, and continues term after term. Often, each new term changes the answer by a smaller amount than the term before it. To understand this gentle process, imagine walking toward the center of a circular courtyard. First, you cross half the distance. Then you cross half of what remains. After that, you cross half of the smaller distance still left before you. There is always another possible step, yet the steps steadily diminish. Together, they do not carry you away without limit. They bring you closer and closer to the center. Mathematicians say that such a process converges. Convergence means that as more terms are included, the result approaches a particular value. The process may have no final term, but it can still have a well-defined destination. Between roughly the 14th and 16th centuries, mathematicians associated with Kerala, on the southwestern coast of India, developed powerful ways of working with these endless processes. Their mathematical tradition is now often called the Kerala school. These scholars studied mathematics and astronomy. Their work with angles, arcs, and circles encouraged careful methods for trigonometry and pi. Rather than seeking only one useful fraction, they explored calculations that could be extended as far as patience and practical need allowed. Among the most significant figures associated with this tradition was Madhava of Sangamagrama. He probably lived from around 1340 to 1425. Direct writings by Madhava are scarce or lost, and much of what is known about his achievements comes from later Kerala scholars. Those scholars credited him with foundational results and preserved accounts of his ideas in their own texts. For that reason, historians speak with care. The tradition strongly connects Madhava with these discoveries, although much of the surviving evidence reaches us through later hands. Knowledge, like a lamp carried through the centuries, may remain visible even when the person who first lit it can no longer be seen clearly. Madhava and the mathematicians who followed him developed infinite series equivalent to expansions now associated with arctangent, sine, and cosine. These trigonometric functions describe relationships involving angles. Sine and cosine, for example, can express the changing height and horizontal position of a point moving around a circle. Arctangent works in the other direction, helping to recover an angle from a numerical relationship. One series connected with arctangent provides a route to pi. In modern language, a special case begins like this: 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, continuing onward through the odd numbers, with subtraction and addition alternating in turn. If this series were continued forever, its value would be 1/4 of pi. Multiplying the result by 4 would therefore give pi itself. The opening steps are simple. Begin with 1, subtract 1/3, add 1/5, subtract 1/7, then add 1/9. Each term is smaller than the term before it, and the total shifts back and forth around the value it approaches. One partial sum may lie a little too low, the next may lie a little too high. Gradually the movement becomes narrower. A partial sum is simply the result obtained after using a limited number of terms. Although the full series continues without end, every written calculation must pause somewhere. A scribe may stop after 10 terms, 100 terms, or some other chosen point. The answer at that moment is not the entire infinite sum, but it may be an approximation to it. This particular series approaches pi rather slowly. Even after many terms, it may not give as much accuracy as a patient calculator would like. The Kerala mathematicians did more than recognize the endless pattern. They also developed correction terms and related methods that improved the result. A correction term accounts for some of what remains after the written calculation has stopped. It is rather like pausing on a long road and estimating the distance still hidden beyond the next bend. The traveler has not walked the whole way, but careful knowledge of the road can still reveal how much farther the destination lies. This was an essential part of making infinite series useful. No human hand can write infinitely many terms. Every practical calculation must end. To work effectively with an endless series, mathematicians needed to understand not only the rule that generated its terms, but also the likely size of the error left after stopping. Other series developed within the Kerala tradition described sine and cosine. In these calculations, powers of a chosen quantity were combined with carefully arranged fractions. The pattern could continue indefinitely, while successive partial sums approached the desired trigonometric value. In this way, a curved relationship could be approached through familiar acts of arithmetic. Multiplication, division, addition, and subtraction were repeated with care. Each finite line of writing became part of a pattern that extended beyond the page. The finite and the infinite had come into quiet contact. An endless process did not require anyone to complete an infinite number of steps. Instead, it could be understood through a rule and through the way successive results drew nearer to a stable value. This was a different way to approach pi. Earlier geometers had enclosed circles within polygons and increased the number of sides. Other mathematicians had found excellent fractions, such as 355 over 113. Infinite series offered neither a many-sided shape nor one fixed ratio of whole numbers. They offered an unending sequence of adjustments, each one refining the result that came before. Centuries later, infinite series became central to calculus and mathematical analysis. Similar expansions became widely known in Europe under the names of later mathematicians. The Kerala work, however, arose in its own historical and intellectual setting. Surviving texts show that mathematicians in southwestern India had explored these ideas well before those later European formulations. The history of mathematics is not one straight road traveled by a single culture. It is more like a broad landscape crossed by many paths. Observation, inherited teaching, practical calculation, and individual insight can lead different communities toward related ideas. Some writings survive intact, others are lost. Still others remain only through quotations, commentaries, and explanations preserved by later scholars. Along the Kerala coast, enough was preserved for us to glimpse an important change in the story of pi. A circle could now be approached through a calculation that continued in principle without end. Term followed term. Each addition or subtraction adjusted what came before. The movements became smaller, and the result settled ever closer to its destination. The written calculation always had to stop. The mathematical pattern did not. It continued quietly onward, through smaller and smaller changes, converging toward the constant held within every circle.